Okay. So far in this course we have looked at mostly search based methods in one form or the other, but if you look at human beings are essentially knowledge based creatures. By this I mean that we very rarely do search, or we rarely do trial and error, unless of course you are doing research or something, which is a different matter. But by and large in everyday activity we look at a problem or we look at a situation and we instinctively do something. And when I say instinctively, what I really mean is that we already have lots of experiences stored in our heads, and we also have lot of rules that we have acquired over a period of time. We know exactly what to do. For example, if it is raining and if you happen to be carrying an umbrella, you instinctively open it. You do not plan and say that if you open an umbrella and keep it over your head, then you will not get wet. In fact, you do not even reason about a goal, saying that you have a goal of not being wet essentially. So, a lot of time we simply use knowledge. So, we want to now spend the rest of the semester looking at knowledge based approaches. In particular, we will look only at a specific kind of knowledge representation, which is logic based, but let us start off with a more general representation. Okay. So, essentially you can associate the word knowledge with to know, that you know facts, you know how to solve problems, you know how to play tic tac toe, you know how to ride a bicycle, all kinds of things are known to you essentially. And if a agent is to interact in a with its world or with its surroundings in an intelligent way, then an agent needs to represent its surroundings, create a model of its surroundings if you want, and reason with that model essentially. Not necessarily a model which reflects how the world is around us, but some form of representation which helps us solve problems essentially. So, if you remember, we had said that when these philosophers 200-300 years ago, they were wondering about what is mind, what is thinking. They said, Hume and Descartes and Hobbes, they said thinking is meaningful manipulation of symbols. So, if you recall this, we are sort of coming to this approach of what we mean by thinking. Of course, when we did search, we also did meaningful manipulation of symbols, in the sense that we created a representation of the state space, we created a representation of the move gen, and we sort of did some manipulation which would take us from the start state to the goal state. But now we are talking in a more general sense. So, manipulation of symbols. Also recall the physical symbol system hypothesis, which we had talked about in the very beginning. Simon and Newell, they said the ability to manipulate physical symbol systems is sufficient to create intelligent behavior. And what we meant by physical symbol systems, so symbol systems of course we understand, these are structures of symbols. By physical, what they meant was that they obey some kind of laws of reasoning. So, which is also sort of ties up with this idea of manipulation of symbols. The only question that remains is about meaningful. We will try and get some insights into this as we progress, not necessarily today, but maybe in the next week. But let us focus on the fact that what we mean by thinking is representation of our situation or the world or the surroundings and the goals and the desires and anything, and thinking basically means manipulation of those representations. Now, if you sort of bring it down to simple computer science terms, it basically means we want to do some kind of representation, data structures we want to devise, and wherever we have data structures we need to have algorithms. So, manipulation of symbols will be done by algorithms, and in that sense the word physical fits in there, is that we have well defined ways of manipulating symbols. which obey some laws essentially. What is the kind of knowledge that we carry in our heads? Okay. The simplest is natural language. Natural language is a medium for representing knowledge and even exchanging knowledge essentially. Of course, it started off as a medium for exchanging knowledge, but as people devised means of writing and printing books, it also became a means of representing knowledge, so that somebody else could read it at a different point of time. Why do not we use natural language as a representation mechanism for knowledge? The main reason, as we probably have discussed earlier, is that it is ambiguous. It is not straightforward to understand what one is saying in an unambiguous fashion essentially, because the language is so rich. First of all, you can say the same thing in many different ways, and secondly, if you express something, if you utter something, for example, if I say she walked over towards the terminal, it is not clear entirely what I mean by this sentence. Or if I say he went towards the bank, again it is not clear what I mean, because the words bank and the words terminal have more than one senses, more than one meaning essentially. A terminal could be a terminal in a lab, a computer terminal. It could also mean a terminal in an airport essentially. So, we do not know what we are talking about. Likewise, bank could mean a river bank, or it could mean a financial institution. This is only words which have different senses, but other things like verbs also have different senses. We saw an example, time flies like an arrow. I think we had discussed it at the beginning of the course. It is a sentence which for us seems unambiguous, but if you were to look at it dispassionately without the background context that we always carry in our head, it has more than one parses essentially, and we discussed maybe one or two of them. Maybe I would encourage you to look at them again. But for various reasons, natural language is not, at least yet, a medium of knowledge representation, though eventually we hope that we will equip our machines with enough language processing capabilities to talk to us in our languages, English, Hindi, Tamil, whatever, and represent knowledge also in those languages essentially. Then we do not need to program in C++ or Python or Java or any such thing. You could simply talk to them in English, but that is way in the future. We saw other mechanisms for representation. So, I am talking about representation here. It could be natural language. We have seen rules already essentially. When we studied rule based systems, we said that you could capture heuristic knowledge in the form of rules and then use that. In fact, it turned out that rule based systems has become like a programming language in itself essentially. We also saw something similar to rules when we were talking about planning. The planning operators had the similar flavor about rules, that there was a well defined language in which you could describe the preconditions, and then an action basically linked preconditions to post conditions essentially. But there was a well defined language. So, we were moving towards more systematic ways of representing things. There could be other mechanisms for representing things. You could have tables, for example, log tables. I do not know how many of you have used log tables, but when I was a student, that was a primary means of which you needed to carry to your exams. If you wanted to do some sophisticated computation, you needed a log table and something called a slide rule. I do not know whether you have heard about it, but these are representations of knowledge in some sense essentially. Then it tells you that for this number the logarithm is this, for this number the logarithm is this, and so on essentially. Then we have knowledge embedded in procedures, and typically an imperative program contains a lot of knowledge which is not explicit essentially. We may have written a program to create the to compute the eigenvalues or eigenvectors, or to find roots of an equation. All these programs contain knowledge which is your knowledge, which has been put into the program, and henceforth when the program runs, basically it is executing your instructions. Knowledge is not explicit essentially, and I do not know whether we had discussed this sometime, but the view that was propounded by Kowalski, Robert Kowalski. He used to teach in Imperial College London. 1970s, he was the inventor, one of the inventors of the programming language Prolog, or the idea of logic programming. He said that a program is equal to logic plus control. That a program, computer program, has two components. One is what you might call as business logic, or the domain logic, or the problem solving strategy, and the other is control, essentially what statements to execute in a program essentially. And the view in logic programming community is that control should be left to a system, in our case an inference engine. So, Prolog will basically, as we will see rather, basically does depth first search over a representation. But we have seen a variation which is rule based systems, which is a forward chaining system, where you write rules and everything that you want to say is expressed in the form of rules. So, you can associate logic with rules and control with an inference engine. So, we studied the Rete algorithm for representing representation of rules, and then we saw the match resolve execute cycle, which forward chaining does essentially. So, that is separating out. So, the control is left to the inference engine, you only provide the logic essentially. But very often in our imperative programs, C programs especially, whatever you do is embedded inside procedures. So, that is another form of knowledge representation. When you talk about knowing how to swim or knowing how to ride a bicycle, it is almost impossible for you to articulate that knowledge. How do you ride a bicycle? You cannot explain it so easily. It is sort of embedded into some procedures which you have learned over a period of time essentially. So, we also carry such knowledge of course. Then there are things like neural networks, which basically encode knowledge in the form of weights, and we had already observed that these are sub symbolic. They are representations, they are explicit representations, but a symbol does not stand for something in a neural network. A symbol meaning a weight, basically everything in a neural network is recorded in terms of weights essentially. A weight basically tells you what is the connection between one neuron and the next neuron, or what is the strength of the connection between two neurons. It does not tell you how you are representing the concept of a chair or a character or an image or a pattern that you are trying to recognize. We also have things like probability distributions. So, very often we try to represent knowledge in terms of probability distributions essentially. Okay. This is how is the general behavior of a certain class of entities, we say it is a probability distribution. So, this is how a dice behaves, for example, we say that it follows a probability distribution, and if you roll 3 dice at a time, they will follow a probability distribution. So, that is another way of representing knowledge, this thing. What we are interested in is logic, and this is what we will spend our time in the remainder part of this course, looking at logic as a mechanism for representation as well as a vehicle for reasoning essentially. So, whenever we do representation, what is the use of representation if you cannot do something with it? So, along with representation you must have reasoning essentially, and logic provides a very nice vehicle for doing both essentially. So, logic is associated with, on the one hand, with language, and on the other hand with inference, inference procedures, or the capability to do inference essentially. So, before I get into logic, I want to sort of try to create a outline of what are the different kinds of logics that people talk about essentially. One thing common amongst all is that or the language of logic talks about sentences. A key phrase in logic is a sentence, a basic entity in when you are talking about using logic as a language of representation is sentence. So, essentially logics are devised to express sentences in one form or the other, and what is a sentence? A sentence is something which in principle is true or false, or can be true or false. Anything which in principle can be true or false is a sentence, and logic, various logics are devised to represent various categories of sentences, and then of course reason with them essentially. So, what do we mean by something which can be true or false? If I say can you please lend me a book, now that is not a sentence in the sense of logic, because it is not something which is true or false. It is basically a request or imperative statement and saying can you do something for me essentially, or it could be a question mark. So, question marks are not sentences. If I say what is your name, it is not something which is true or false. So, it is not logically a sentence, it cannot be assigned a truth or false value. Or if I say please give me a glass of water, it is not a sentence, it is a request or an imperative statement. Those things are not sentences. Anything which in principle can be assigned a truth or false value is a sentence. So, if I say white wins in chess, or white always wins in chess, and by this I mean when both sides play perfectly, it is a sentence. I do not know whether this sentence is true or false, because as we discussed when we were talking about game playing, the chess game tree is so huge that we have no hope of solving it, at least not in the very near future. So, we can make such sentences whose value we cannot determine, but nevertheless they qualify as sentence. If I say the moon is made of green cheese, that is also a sentence, but in this case you can sort of fairly confidently say that it is a sentence which is false. So, sentences are those things which can be true or false essentially. Now, there are different kinds of languages essentially. So, the simplest kind of language treats a sentence as one unit. So, if I say the earth is flat, then that is one unit essentially, and the simplest kind of logic or logic language which we call as propositional logic treats a sentence as a unit, unbreakable, indivisible unit. You cannot look inside a sentence, you cannot say that this one is talking about something called the earth and it is talking about a property called being flat, nothing of the sort. It simply says this is some sentence, and typically we use, and you must be familiar with this, something like a symbol to say P stands for this, P stands for the earth is flat essentially, or I can say Socrates is a man. This is a sentence in propositional logic. I cannot look inside it, I just say it is something, and then of course, I would want to assign a truth value to this essentially. I can say all men are mortal. This is also in propositional logic, it is just some sentence. I can simply call it Q, I can simply call this R or P1, P2 and so on and so forth, and we cannot look inside sentences. So, a logic in which you cannot look inside a sentence, or where a sentence is the atomic unit, is called propositional logic. And then of course, there are logical connectives. So, you can say the earth is flat or Socrates is a man, or the earth is flat implies that Socrates is a man. You can do all these kind of things, you can combine sentences to form compound sentences. We will see the syntax, and I am sure you are familiar with it. Such logics are called propositional logics essentially. Now, these two statements are well known for anybody who has studied logic, because they together represent some of the oldest examples that people have been using in logic. In fact, from Greek times, that is why we have the term Aristotle, sorry Socrates, and the logic. And the reasoning part says that if you know this, or if this is true, and if you know this, and or in other words this is true, we will use the term interchangeably, then you can infer that Socrates is mortal. So, this is the reasoning part, and this is what we mean by reasoning in logic, is that if you know certain set of statements to be true, or you assume them to be true, or they are given to be true, then you can infer that there are other statements which are true. So, if somebody tells you that Socrates is a man, and if somebody tells you that all men are mortal, then what Aristotle showed was that you should be able to infer that Socrates is mortal essentially. And this particular form of reasoning, or this particular rule, is called a syllogism. We will not go too much into history of logic here, because there is plenty to look at there, but we will just keep in mind that this was there in Greek times as well essentially. In fact, reasoning is the motivation for which logics were invented in the first place essentially, because people wanted to say that we do not want to argue about truth values of statements essentially. If you know something is true and something else is true and something else is true, we should be able to infer that something else is true. So, in that sense, logic is associated with a particular form of reasoning which is called deduction. Okay. And we will come to this again, but just to get started, by deduction we mean making inferences which are necessarily true. Okay. So, that if the premises or the given or the axioms are true, then the conclusion must necessarily be true. Logic is concerned with forms of reasoning which take you from true statements to more true statements, and they take you, and it is a reliable robust mechanism. If a logic machine, and we will talk about that, says that this sentence is true, then you should be able to believe it without any reason. Okay. But there are other forms of reasoning that we often do, which are not necessarily always true. So, experience, for example, is always captured in patterns and conclusions. So, you see dark clouds and you say it is likely to rain essentially. Now, of course, that conclusion you can make, but it is not necessarily true, because you do not know what is going to happen. That is not a logical, that is not something that you can deduce essentially. Or to take a more topical example, if I say this student's signature is there on my sheet, then he is present in the class. Now, that is not a reliable conclusion to make essentially. These are forms of reasoning which are not deductive essentially, and we do deduction, we do other forms of reasoning all the time. We do, for example, generalization. The whole machine learning community is occupied with generalization. You look at some examples, from that you generalize essentially. You look at one leaf, you look at another leaf, you look at a third leaf, and then you come to a conclusion that all leaves are green. It is a form of inference which is not necessarily deduction essentially. Or you look at a crow and you see that the crow can fly, you look at a sparrow, again you can see that a sparrow can fly, you see a parrot can fly, and you come to a conclusion that all birds can fly. This is a form of generalization, it is a form of learning, you might say, but it is not infallible. For example, there are birds which cannot fly, penguins cannot fly. So, there are other forms of reasoning which we do all the time, or look at the process of diagnosis. We saw recently an example of doing diagnosis by a process of consistency checking essentially, but we cannot necessarily say that what we have concluded is a real fault, because in the real world In the real world, a fault causes a symptom. In the real world, something has gone wrong, and therefore, we can see the symptoms of it as it having gone wrong. But in diagnosis, we move in this other direction. We look at a symptom and we jump to a conclusion, or we make an inference that this is a fault essentially. And these are not necessarily correct. So, if you go back to the example that we looked of multipliers and adders, we could have concluded that the one adder was wrong, or you could have concluded that one multiplier had gone wrong. Any of them could have been true. In fact, we could have even said a combination of things could have gone wrong. Any of them could have been true, and without further investigation, we are not able to make a more definitive statement. Medicine is full of this kind of reasoning. You look at symptoms and you make inference as to what has happened to you. You have fever, you have shivering in the evenings, and you jump to a conclusion that you have malaria essentially. Now, this is not deduction, it is not necessarily true. We are interested in logic for deduction, that statements that we derive or produce using this logic machinery should necessarily be true, and logic is built around that motivation essentially. Now, in propositional logic, I cannot take these two statements and I cannot devise a mechanism for arriving at that conclusion, because it is not so straightforward to make the connection. For that, we will have to go to a higher logic or a more descriptive logic, which is called first order logic. And we will in fact spend most of our time in first order logic. In first order logic, we break up a sentence into its parts. We treat the word all separately, we treat the word men separately, and we treat the word mortal separately, and the connection between them separately. We break down the sentence and represent it with constituents, which we can then reason about essentially. So, essentially what we will say is that men is a class of entities, mortal is another class of entities, and if anything happens to be a man, then that must also be mortal. And then from that we will reason that because Socrates happens to be a man, then Socrates is reason. But to do this, we need this machinery of first order logic, which is little bit more expressive in nature. Now, this is a fact of logic, is that the more expressive a language you devise, the more complex is the computational required to reason with that essentially. So, computational complexity increases with expressiveness. So, some of you would have heard about Gödel's incompleteness theorem, and what that theorem says, and maybe we will come back to that a bit later if we get time, is that if languages are expressive enough, then there are conclusions which the logical machinery cannot make. In that sense, it is incomplete essentially. So, we talked about completeness when we were talking about search. There is a similar notion of completeness in logic, is that given the fact that there exists a true statement out there, is my machinery able to reach that true statement or not, is the notion of completeness. And what Gödel showed in 1931, that rich enough languages will never allow completeness. And so, there is a trade off, the more richer the language, the more difficult it is to do computation, and most of the computations that we do including the programs that we write, C programs, will fall into the category of first order logic essentially, and it is characterized by having variables and being able to write loops which use variables and things like that essentially. We will formalize that a little bit later, but there are other kinds of sentences we can talk about. So, we have seen two forms of logic, propositional logic, first order logic. There is also something called second order logic, which is what Gödel's theorem applies to, but we will see if we come to that. But what about statements like this? If I say Nisha is tall, now that is a statement. In principle, of course, I can give a truth value to this by saying that this is true, this could, I could say this is a true sentence or this is a false sentence. But the question arises as to when can I say that this sentence is true. So, logic will also be concerned with semantics as to say that when is this sentence true essentially. Now, the trouble with this kind of sentences is that if I were to devise a rule which says if you are more than 6 feet then you are tall, if you are less than 6 feet you are not tall, then I have this problem that what if somebody is 5 feet 11 inches or 11 and a half inches, is that person not tall and somebody who is just 6 feet is tall? It leads to problems when you are trying to model real world domains and reason with them, that if you want to talk about properties like tall, warm, cool, what do you really mean? Somebody says this room is too warm, somebody else feels it is not too warm. Of course, apart from the fact that there is subjective difference, there is also the notion of we do not really know what temperature does warm begin with and what temperature it is no longer warm. So, do we say that if it is more than 30 degrees centigrade it is warm or it is more than 35 degrees, can we have a crisp boundary? That is the real question essentially. Can we divide things into warm, not warm, tall, not tall by drawing a crisp boundary? And many people felt that that is not the case, that is not what you should do, and one of them was Lotfi-Zadeh, you must have heard about him, who devised this thing called fuzzy logic. So, the way fuzzy logic is different from what is used here. So, these two are what we call as classical logic, and by classical logics we more or less mean two valued logics, that a sentence can take one of two values. In our case we call them true and false, but that is only for our own convenience. But people have thought about multi-valued logic. So, if somebody says maybe you should have 3 values, true, false and maybe or something like that, or true, false and do not know, maybe that is a third value. People have tried to devise logics like that essentially. What fuzzy logic? So, in two valued logics a sentence is either true or it is false essentially, and that is, as we will see, the semantics of a sentence like this says that if you are mortal you either belong to the set of things which are mortal or you do not belong to the set of things which are mortal. So, if you belong to the set of things which are mortal then you are mortal, otherwise you are not mortal. So, that is a crisp set as we say, as opposed to that what Zadeh said was that why do you want to work with crisp sets? You have a notion of a set membership or the characteristic function that you must have defined at some point. Why is it mapping only to 0 or 1? Why cannot it map to 0.7, 0.8 or something like that? And Zadeh said that, for example, if I want to define tallness and this is height, then I should be able to define something like this. Now, at some point it becomes 1, but there are regions where you have different amount of commitment to this belonging to this set. So, set membership or fuzzy sets. So, fuzzy logic comes from fuzzy sets and classical logic comes from crisp sets, which either have membership is 0 or 1. Here membership is a continuum between 0 to 1. So, you can, if you are this height, this is your membership to this set of tall people. If you are this height, this is your membership to the set of tall people, and it varies essentially. There are other kinds of logic which deal with uncertainty. So, for example, if I say Tweety is a bird, can I infer that Tweety can fly? To make these kind of inferences, and we call these inferences defeasible inferences, meaning that the inference can be defeated, that you may say yes Tweety can fly, but somebody will give you some evidence to show that Tweety cannot fly essentially. So, somebody tells you Tweety is a bird and you say Tweety can fly, and then somebody tells you that Tweety is a penguin, then you realize that oh, penguins cannot fly, then your inference is defeated essentially. But most of the time we do make inferences which can be defeated. So, we go to the canteen and assume that I will get tea there, or the canteen will be open, or my bicycle will have air, all kinds of things we believe in which can be defeated essentially. So, the ability to make defeasible inference is very important to us, because otherwise we would never be able to make inferences. If I say, if I use a statement that all students are bright, then somebody comes and shows me one student in some corner of the country who is not bright, then my statement becomes false essentially, because when I say all students are bright, it means that each and every student, that each and every person who is a student must be bright. Now, if somebody shows me one person, not in Chennai of course, who is not bright, then my statement goes is no longer true, which means any inference that I would have used making that statement as a premise, I can no longer make, because the statement is no longer true. So, if I say students in IIT go and take up jobs in Goldman Sachs, by and large right, or something like that. So, ability to make, the ability to reason with statements in which you do not have complete belief, of which there is uncertainty, and then reason with them is very important for us. We use it all the time, and we must develop mechanisms to do that. And some of the things that of course, we will not study it in this course are things like default logics and default reasoning essentially. Then we make other kinds of statements, which, so we may want to make a statement of this kind, that maybe let us say we are sitting in this room and we hear some sounds, and then we make an inference, we make a statement that it is raining essentially. Of course, we do not know whether it is raining or not, but we can make a statement that it is possibly raining. What do you mean by truth values of such sentences? How do you evaluate a truth value of such a sentence? If I say it is raining, you can go out and look outside the window and say that the statement is true or the statement is false. But what about a statement like it is possibly raining essentially? Or if you say that maybe he is sleeping in his room essentially. So, of course, you can, in this particular case, you can go and check whether the person is sleeping in his room, and then you can have a new statement which says he is sleeping in his room. But what can you say about the statement maybe he is sleeping in his room? Is that a true statement or a false statement? Now, people have tried to devise logics. Well, I do not know what you mean when you say true statement. So, you have to be a bit careful essentially. When you say it is a true statement, then what one should say is that there exists a possible world. So, if you assume that everything that you do not know, we have only a finite amount of knowledge about the world essentially. Then if there is a possible world or a feasible world or a consistent world in which that statement were to be true, then we can accept such a statement to be true. So, it is a little bit not easy to discuss right now, but we have this kind of a notion that it is possibly true or it is necessarily true. So, in fact, there is a whole logic which is devised to talk about statements of necessity and possibility essentially. So, for example, you might say in diagnosis that it is possible that he has malaria essentially, and these logics which are called modal logics allow one to talk about statements like this essentially. So, we have something called modal operators, and there are in particular two operators. One is called diamond operator. This is standard usage in the modal logic community, and the other is called a box operator. And if you write a statement like diamond P, it basically means that P is some statement like this. For example, the earth is flat. If I say diamond P, it means it is possible that the earth is flat essentially. So, I have a language for expressing this essentially, and then they have mechanism of reasoning with such statements essentially. One particular kind of modal logics is temporal logics. Where so temporal of course deals with time, and when you deal with time and you are talking about the future, now you know that not all the time you can make definitive statements. So, if the world is if the sky is cloudy, then you can say it will possibly rain essentially in the future. But temporal logics are even more tied to time, and you can make statements like if you leave a block of ice on your table, you can make a statement that it will eventually melt essentially, that there will be some time in the future when the block of ice will no longer be there and it will melt essentially. So, you can reason about time essentially, or time and change and things like that essentially. So, you can say that if you keep giving proxy, then eventually you will get a W grade essentially, of course not today. Now, another kind of temporal logics deal with statements like the following, that John knows something something. So, John knows that the earth is round. Now, look at this statement. This sentence contains a sentence. So, that is the first thing you should observe, that there is a sentence inside this, the earth is round, and okay, well I had P here. So, let us call this P1. Now, what I am saying in this sentence is that John knows P1 essentially. So, such logics are called epistemic logics, and I would basically represent this statement in a simple epistemic logic as saying that K j, where K j is a modal operator which says that John knows something, and then that sentence P1. So, one can now talk about someone knowing some things, but one can also talk about statements like this, that this is another sentence in this epistemic logic, and let us say M stands for Mary. What this sentence is saying is that Mary knows that John knows that the earth is round, and of course, you can now have all kinds of things. You can say Mary knows that John does not know that Peter has gone home, all kinds of statements. So, you can combine logical operators which we have not seen so far, but we will see them in due course. So, what modal logics are doing is that they are taking some standard logic, and in our case it is propositional logic that we are talking about, then applying modal operators. So, these are modal operators which talk about necessity and possibility. It is possible that Mary loves John, if I want to say, then I could use a diamond operator essentially, and or I could use a this operator. Temporal logics use modal operators which talk about time. Epistemic logic use modal operators which augment the language by talking about what people know essentially. Now, almost similar to knows is the notion of belief. So, people have built logics which talk about belief essentially. What is the difference between knowing and believing? Well, we would like to say that if you know something, it is necessarily true. If you believe something, it may not necessarily be true. So, I can say Peter believes that the earth is flat essentially. That is a perfectly valid true statement, because that is what Peter believes essentially. The earth may not be flat, but the statement is a true statement essentially. So, belief, so knowledge and belief of course is quite an interesting thing to work with, especially when you are talking about multi agent scenarios essentially. In fact, epistemic logics were created to handle multi agent situations. If you have many agents, if you have networks of agents and they are doing certain things, then how can we reason about it? How can we show, for example, that given a certain protocol, a group of people will always elect a leader or not elect a leader, or will be unable to elect a leader? How can we prove such things essentially? This is what people with epistemic logics have been. Associated with possibility and necessity is a mathematical foundation called rough sets essentially. So, just like fuzzy sets form a basis for fuzzy logic, and fuzzy sets are sets in which membership can vary to degrees. Rough sets are sets which have basically two boundaries essentially. So, for example, if I say I am talking about the set of tall people, then I could draw one boundary here and another boundary here, and the meaning of this is that everybody anything inside the inner circle is definitely tall, necessarily tall, and anything inside the outer circle, but outside the inner circle is possibly tall, but not necessarily tall, and anything outside both the circles is not tall essentially. So, rough set is a mechanism which has been devised to deal with this kind of uncertainty essentially. Now, the last form of reasoning that is not so much like logic, but we have probabilistic reasoning. So, probabilistic reasoning is one way of handling uncertainty essentially. So, for example, when you are doing diagnosis, for example, you might devise a system which says if somebody has some symptoms and somebody has yellow eyes, then it is likely that the person has jaundice. How do you express this fact that it is likely? Because one thing is this possibility, but if you want to now talk about gathering evidence and increasing your belief in something. So, you believe that this is really the case, maybe you do one more test and your belief increases. Probabilistic reasoning is one mechanism for handling uncertain knowledge essentially. Okay. Now, you must distinguish between fuzzy logic, which also is talking about numbers which are less than 1, and probabilistic reasoning which says my conclusion, I am 70% sure of my conclusion or something like that. There is a difference between this and fuzzy reasoning. In fuzzy reasoning, it is a question of, it is a linguistic problem really, as what do you mean by the word tall essentially, because it is not defined clearly. Whereas, in probabilistic reasoning, if you say that the chances that he has jaundice is 0.7 or the probability is 0.7, then you are saying that this is a way of talking about my lack of knowledge about the real situation. So, of course, you know that when you throw a dice, you say the chance of it falling 1 or 2 is 1 by 3, it simply says that because I cannot say what it is going to fall in the future, I just use probability as a mechanism for expressing my lack of knowledge about what really is the case essentially. If you had perfect knowledge about physics and all the information that is needed to do the calculations of what was really going to happen when you throw a dice, then between the moment when you throw it and the moment when it really falls, you should be able to compute in principle whether it will fall with 1 or 2 or 3 or 4 or 5. But of course, we do not have that knowledge, we do not have the computation ability. So, we say talk about probabilities, it is likely that it will fall like this, or it will fall like this essentially. If you get time, we will look at a variation of probabilistic reasoning in the context of diagnosis and see that when you get multiple pieces of evidence, how do you combine those evidence to maintain a different amount of belief in all kinds of things. But that will be towards the end if you get time. In the next class, we will look at propositional logic more formally. In fact, when we talk of logic, we always use the term formal logic, because logic is concerned with form and not with content essentially. Logic is concerned with valid forms of reasoning, and it is not concerned with what you are talking about. So, I can say that Socrates is a man and all men are mortal. The syllogism allows me to conclude that Socrates is mortal. If I say Ramesh is a student, all students are bright, then the same form of reasoning will allow me to infer that Ramesh is bright essentially. And why is that a valid conclusion? Because the form of reasoning that I am using, which Aristotle called as the syllogism, he showed to be a valid form of reasoning. So, we will look at valid forms of reasoning that we will use in propositional logic and try to show why they are valid also in this thing. So, we will start off with the language and then we will look at the mechanism for reasoning, and this whole thing we will call as a machinery of logic. So, we will in the next class try and build a small machinery for propositional logic essentially. And then the rest of the course will spend on first order logic essentially, because that is really more interesting. Okay, so I will stop here I think.